The first question, I believe, let me find where that was. I want to scroll through these slides. I went through these and tried to identify where there were questions. All right, good. The first time anything like a question appeared in the slides was on slide 23, right here, which asks what happens if you change dt, t-stop, and points plotted per millisecond. I assumed some of you would ask, or if you didn't ask, you'd do one of these things and try to figure out what had happened. So let's proceed with examining what are these names, what do they mean? So as we discussed, I think last time, t-stop and dt are simulation parameters. They control what happens in the course of a simulation. dt is the interval between points in time where a neuron calculates a new solution. And t-stop is the time in model time when it will stop. So if t-stop is 5 milliseconds, then you'll get a simulation that'll run from t equals 0 milliseconds to t equals 5 milliseconds, okay? And if dt is 0.025, then neuron will generate a new solution point every 25 microseconds, which would be 40 times per millisecond, so you'd get a total of 201 data points. One data point at 0, 0, and the final data point at 5 milliseconds, okay? Now, points plotted per millisecond is a little different. It actually controls the appearance of the graphs you see on the screen. Specifically, it controls the intervals at which new points are added to graphs, okay? So it's the plotting interval is the reciprocal of points plotted per millisecond. So if points plotted per millisecond is 40, which it is by default, then neuron will be plotting 40 points to your time axis graphs per millisecond. Okay, so any graph that shows a variable plotted versus time, there will be 40 new data points per millisecond of simulation time. And of course, that's simply the reciprocal of points plotted per millisecond. Now, if you look at this, if you look at dt and points plotted per millisecond, you realize that actually these are not independent parameters. They have to agree. That is, the plotting interval has to be a whole multiple of dt. So a neuron can't advance 2.5 simulation steps and then plot 2.5 points, okay? So what you have to have is some kind of an integer relationship between them. In particular, you have to have a whole number of time steps between the points that are plotted to the screen. Okay, so and at initialization, neuron checks dt to verify that dt has an appropriate value, and if it doesn't, it makes dt change to a value that is closest to whatever it started out as, that solves this Diophantine equation where I is a whole number, okay? So if points plotted per millisecond is 40 and dt is 0.025, you're fine. And if it's 40 and dt is 0.0125, you're fine. But if it's 40 and dt is 0.01, you're not, and neuron will automatically change dt to a value that agrees with points plotted per millisecond. In that case, it would change it to 0.0125. probably 0.0125. Okay. All right. The next question, are there questions about that? If you do have them, post them in Ask Tutors. Okay. So let's go back here and step through and look at our next question. Oh, there we are, slide 25. What stimulus current depolarizes the model by 10 millivolts? Okay, well, we're using our single compartment model. So let's go to that. Okay, so we had our model cell, our single compartment model cell. Let me shrink this down. Get this back up here. And I'm going to do Python 3 minus I, and it's going to be simple cell.py. Well, by the way, before I do that, I should show you what simple cell.py contains. Simple cell.py, see if I can make this, maybe I should make this a little bigger. Okay. And I can close that. Okay, so there's what simple cell.py consists of. Those two statements. The first one makes Neuron available to Python as a module so that all of Neuron's variables and methods are accessible to Python. And the second one loads the session file that saved all my graphical tools that I used to create the single compartment model cell and to work with it. So now let's actually do that. Python 3 simple cell.py, and there is our model cell ready to go. We can look at it. That's what it looks like in its cartoon. And I'll drag this out of the way. And if I run a simulation, I see that initially the cell is starting out at, if I put my cursor down here and then click on that, I see it initially the cell is at minus 65 millivolts. That's the meaning of that minus 65 you'll see. And then at the end of the current pulse, it has zipped up to 34.99, let's call it 35 millivolts. So it's gone up by 100 millivolts. And the thing that I was trying to accomplish, I want to make that be, say, 10 millivolt depolarization, not 100. So this is a linear model. It has no active currents, nothing nonlinear in it. So if I go down here to the point process manager, which generates the current pulse, and I expose the parameter page by clicking on show parameters, I can click in that numeric field, and I can change that amplitude by a factor of 10. I'll divide it by 10, and I can run another simulation. And there I see the cell now depolarizes from minus 65 to minus 55. Okay. And if I wanted to rescale this graph, I could click in the menu box, go up to view equals plot. There we are. And there we are. We see it going from minus 65 to minus 55. And if I wanted to make that trace stand out and be a different color, I could click on the menu box, scroll down to color brush, make that red and thick, click on the label, and then I can click on the menu box again and go back to crosshair. So now we see our voltage axis trace. And what current is it that did that? Well, let's do view equals plot here. View equals plot in this graph. Oh, it's a current pulse that is, that's interesting. 0.01 nanoamps. The original value was 0.1, and 0.01 cuts the amplitude down by a factor of 10. Good enough. Okay. Let me change these preferences. It's a little too big. Go back to appearance. Change this back down to something more manageable. There we go. Close. That's better. Okay. All right. Admit. Letting in somebody. So now let me look at our next question. And there's the PDF, and I'm having a little difficulty dragging this around, so I'll just have to wait for things to become less busy. Maybe, good. Okay, so there we are. The 0.1 nanoamp times 1 millisecond current pulse drove it 100 millivolts depolarized. Linear model, so cutting the amplitude to 0.01 nanoamps should reduce it to 10 millivolts, and it does. Okay, good. Now, slide 26 is the next slide to have a question in it. Actually, it has several. When we added pass to the model cell, what did it do to the model cell's resting potential? Well, let's go back to our cell builder. And let's add pass. So we do that, we click on the geometry radio button. Come on, geometry. Uh-oh. Things are getting a little slow here. I'm outpacing the user interface. Don't like that a bit. This did not happen last time. Okay, so I'm going to have to do something here to speed things up. Let me stop share for a moment. Maybe I can, no? I can drag that. I can drag that. But I'm not able to do anything. Biophysics, finally, at long last. Okay, go back to biophysics, go to the specify strategy view of biophysics page, and let's add pass. Okay, and now what happens when I run a simulation? Okay, well, what did it do? Well, what we see it does is it changes, first of all, resting potential of the cell, and it also changes the dynamics of the cell. So instead of the cell following the injected currents waveform, there's a first order lag behind it. Okay, and that means that actually it didn't follow it before either. It had a ramp. So we have a first order lag behind our nice square pulse. And okay, can I go back to my PDF? Okay, so here I'm in the PDF. Is it useful to initialize a model to its resting potential? Yes, we talked about that on Thursday last week. Experimentalists do this by letting their brain slice or their surgerized animal have a rest interval before they start doing experiments. We as modelers can do that by trying to do custom initializations. In this case, the custom initialization consists of recognizing what the reversal potential of the passive mechanism is. The passive mechanism has a reversal potential of minus 70 millivolts, and if there's no other ion channels present, the cell is going to want to rest at minus 70 millivolts. So we can subtract 5 and do another simulation. And now we start with a nice stable resting potential before the injected current pulse starts, okay? And as you may remember, the way we can discover what the resting potential of the cell is, if the cell is not starting out at a resting, at its proper resting potential, is we can just run a simulation that lasts a long time, okay? And in this case, we could simply turn off the stimulus, okay, make the duration of the stimulus 0, run a simulation, and let that run time be very long, run that simulation, and then find out what's the stable resting potential. Starts out at minus 65, falls down to minus 70, so that's the value we want, minus 5. Okay, so you'll notice that the default initialization strategy in Neuron is what's called a steady state under voltage clamp. It's as if we voltage clamped the entire model cell, everywhere in it, to whatever this value is for an infinitely long period of time. Everything comes to rest, and then when we run a simulation, everything continues at rest, okay, because it's at its steady state. All right, now I restore the current pulse, and I'll restore the runtime. All right, what would happen to a real cell if we applied an amp of current to it, if we tried to do that? Well, if you injected 1 amp into a real cell, you'd kill the cell, you'd probably blast the electrode out of the electrode holder, and you'd probably fry the electrode preamp. And you might be asked to go do your graduate work or postdoc work elsewhere. With fixed time step integration, actually, well, in a model, we can do anything we want, and the cell will tolerate it because it's only a fictional cell. So now what happens if the next question is, what happens if we change the duration to 0.01 millisecond? Okay, and if we change the duration to 0.01 millisecond, you notice that there's now no response at all to anything. There's no stimulus anymore. Why is that? Because we're using fixed time step integration. Our time step duration is 0.025 milliseconds, not 0.01. And when you do fixed time step integration with a stimulus that is shorter than the integration step, then the stimulus is ignored, okay? If we wanted to really see that stimulus do something to our model cell, we would have to change dt. Now remember, if we try to change dt to 0.1, Neuron won't let us do that because points plotted per millisecond is what dominates here, okay? Points plotted per millisecond is the independent variable here, and when Neuron initializes, it forces dt to a value that is commensurate with points plotted per millisecond. So if we wanted to have a dt of 0.01, we should actually change points plotted per millisecond to 100. And that changes dt to 0.01. And now we can run a simulation, and we see a brief current pulse, and we see a small step here. And if I make the amplitude 10 times larger, it'd be a larger current step, a larger voltage step. And if I make it 5 times bigger than that, it'll even be bigger. Okay, so if you have too short of a stimulus duration, you won't see any effect in your model cell, and that means you need to make dt smaller. Okay, all right, let's go here. Okay, well that takes care of making the stimulus effective. Let's go to the next slide. That was conservation of charge. Where is, okay, where's the next time a question arises? Here we go, in our squid axon model. Adjust the pulse amplitude to find the spike threshold to 2-place precision. Okay, how many of you actually did that? A show of hands? Oh, okay. Good. All right. Well, that's better than nothing. So let's quit our cell here and let's start our hhaxon.py. Before I do that, let me show you what hhaxon.py contains. And it contains from neuron import HGUI and then load file hhaxonrig.ses. And the hhaxonrig.ses is what I generated last time when fooling around with the various graphical tools that made the axon and then attached stimulators, graphs, etc. to it and a run control panel. So let me just do Python 3 hhaxon ses. Whoops, my mistake. Py. Python can't parse a session file. It doesn't understand Hoke, but it understands Python. There we go. All right, so there's our experimental rig. We've got a run control panel. We've got a couple of graphs. One is showing voltage at 3 points along the axon. Another one shows voltage along the length of the axon as a function of time. And there's our user interface for our stimulator and our init and run button that gives us a movie run. Okay. All right, good. I clicked on stop to stop that. So how do we find the threshold? Well, a good way to find threshold is using what's called a binary search. Okay. And one way to do a binary search is, since we're looking for spike threshold, the first thing we need to do is find a stimulus amplitude big enough to give us a spike. And this amplitude obviously does. So the next thing you do is you cut it in half. Cut the stimulus amplitude in half. Do you still get a spike? No. So we know threshold must lie halfway between there, somewhere in that range of 75 to 150. Okay, so let me say 110. Try that just for the heck of it. We get a spike. So somewhere between 75 and 110 is the spike threshold. Let's try 90. Roughly halfway between. Too small. So 110 gave us a spike, 90 doesn't. Let's try 100. 100 gives us a spike, 90 doesn't. Let's try 95. Somebody is saying for this exercise, stimulus duration was 0.1 milliseconds, not 1 millisecond. Isn't that so? You're absolutely right. So let me do that. Let me change the stimulus duration to 0.1. Okay. And that's not going to get us a spike, so let me make it 10 times bigger. We've cut the duration by 10. There we go. So it's between 10 and 100. And let's try 600. 10 and 1,000, 100 and 1,000. 600, let's try. Nope. Let's try 800. Nope. Let's try 900. Yep. Let's try 850. 875. 865. Whoops, that's way too big. 860. Okay, let's try 855. Let's try 858. 857. 856. Okay, so we know it's bigger than 850, and if we want two-place precision, then 860 is what's going to do it. Okay, so I'll say 860. Okay, so we're getting a spike. Okay. While doing this exercise, since the shape of the signal at the source was weird, I looked at the propagated signal to a certain generation of a spike. Is that correct approach? Well, I would do it that way. I mean, I've already got the graphs, so why not? I mean, I'm seeing membrane potential halfway down the axon and also at the very distal end of the axon from the stimulus. So, we know that there's a spike and we know that it's propagating. Okay, so the thing is we want to set it to twice threshold. So if I set it to 2 times threshold, it'll be times 2. Okay, and now I want to measure the spike amplitude and half width at axon of 0.5. Well, that is membrane potential of the axon at 0.5 right there. It's the black trace. And if I just grab that trace with a cursor, I can look at it and I can see that it's at 37.55 millivolts. And if I add that 37.55 plus 65, because it's above a level of minus 65. So the peak is 102.5 millivolts above the initial membrane potential, the resting potential. So we have a 102.5 millivolt spike. That's the peak amplitude of the spike. Now, what's the half width? Does anybody know what a half width is? Well, the half width is the width of a waveform measured at its half amplitude point, okay? Halfway between where it started and its peak amplitude. So let's take a look at that. Spread things out a little bit so it's easier to see. And what is halfway between minus 65 and the peak of the spike? So it would be there we are. It's minus 65 plus, and we said it was 37.5 or 37.6. So the sum of those is minus 27.4, and if we divide that by 2, you can use the keyboard's edit keys to scroll back and forth, and you can add parentheses in front of things and parentheses after things, and you can do arithmetic in the terminal here, which is what I'm doing. So we want to measure, when does the waveform rise above minus 13.7 millivolts on the way up, and when does it fall below that on the way back down? So I'm going to put my mouse cursor on there, minus 14 approximately as I drag it up, and then as I come back down on the other side, again, minus 14, minus 15. Okay, so it's a little bit after it rose past 13.7 and a little bit after it fell on the way down. And so these are the 2 times at which it crossed minus 13.7. So the half width is going to be what? Oh, what prints the coordinates of the terminal? Hit the space bar. Hit the space bar. That's your shortcut, okay? And so what we have is we have these 2 values here. Let me get back my control of my computer. So it becomes 4.75 minus 3.125, and that's 1.65. 1.65 milliseconds is the half width of the spike. Okay, there we go. Cut the sodium channel density in half. What happens to spike amplitude in half width? Okay, well, how do we cut the sodium channel density in half? Well, one way to do it, we can go back to our cell builder, click on biophysics, click on HH. There's our sodium channel density, 0.12 Siemens per square centimeters. I click on that numeric field and do /2. Now I have cut the sodium channel density in half. And what do you think is going to happen? Well, let's do another simulation and find out. Okay, well, these spikes don't look as healthy as they did before, do they? If there's any doubt about that, let's go back to the original value. I just cleared the checkbox on GNA bar HH, restoring the previous value. Do a knit and run. Let's do a keep lines. And that'll keep those traces. And now let me come back down here and click this checkbox again. That'll cut GNA bar HH by half. And I do another knit and run. Okay, so we have reduced the sodium, reducing the sodium channel by a factor of 2 causes a reduction in spike amplitude, slows the spike propagation. You'll notice it takes longer for the spike to get from one point to another, and it changes the half width. So let me do an init and go back, get rid of keep lines. So you see I've toggled keep lines off. Now we'll do an erase. Click on the menu box, scroll down to keep lines to turn it on. When you're ready to get rid of keep lines, scroll down, turn it off. And then if you need to erase stuff, scroll down and erase. All the time, clicking on the menu box first. The menu box is that little square box in the left upper corner of your graphs. Okay? All right, so we're ready to do a simulation that we're going to use now to measure the half width and the spike amplitude. So let's see what the spike amplitude is. It's starting out at around, that's still about minus 65. And that's 22. So it's 22.5 plus 65, approximately 87 millivolts compared to 102 before. And what's the spike width? 22.5 minus 65, and divide that by 2, that's minus 21. So let's find out when this curve passes minus 21 on the way up. There it does. And let's find out where it passes minus 21 on the way down. There it does. So what's the half width of this thing? It's 5.4 minus 3.95, 1.45 milliseconds. And what was it previously? 1.65. So it did reduce the duration of the spike slightly, and it reduced the peak amplitude of the spike. Good enough. Okay, repeat until GNA bar is so low you don't get a spike. Okay, let's cut GNA bar again in half. Boom, 0.03. And now let's run a simulation. No spike. Do you think maybe our stimulus amplitude isn't big enough? I mean, it looks like that's trying to do something there. Shall we increase the stimulus amplitude and just see if it makes things a little, let's try 2000. Getting a little edgy there. Maybe let's try 2500. Ah, so you can see we can elicit the spike. We just have to blast the cell really hard. And it's pretty clear that amplitude is smaller, and it's pretty clear that half width is much bigger now. Is there a way to change half width without changing the spike amplitude? That'd be pretty hard to do. Might be able to do something by changing the operating temperature. We haven't talked about temperature, but Neuron has a parameter called Celsius, which is the operating temperature. And if your model cell contains mechanisms that are temperature sensitive, you can change their dynamics by changing the value of Celsius. So let's go back to normal sodium channel density, do a knit and run. There's our normal looking responses. I'll turn on keep lines. I'll turn it off, and that will preserve those traces for us. And let's say our squid is in a really cold winter, and we're going to change Celsius to, say, 2 degrees centigrade. Okay. Oh, look at that. The spikes are just about twice as wide, and their amplitudes are pretty comparable. So there you go. If we tossed a few ice cubes in with our squid axon, we could make the spikes wider without changing the spike amplitude. Of course, we should make sure that those ice cubes contain potassium and sodium and chloride, or else we're going to be making the seawater dilute, and our squid axon won't be too happy about that. Okay, there we go. All right, I think we've addressed that one pretty well. Let's see, what else? Yes, get a spike. Spike GNA bar must be at least. Yeah, that's true. GNA bar must be at least that value at 6.3 degrees centigrade. So let's go back just to make it normal. Okay. All right, so this part here I showed, well, did I call it axon rig? No, I didn't call it axon rig.py. I simply called it hhaxon.py. And you'll see what it contains. And this is good to do if you haven't done it already, because then you'll be able to run your simulations without having to do an hload file and doing from Neuron import GUI yourself. Let the computer do that. Okay, now it's going to get interesting. Set both current clamps to deliver an effective stimulus, 2 times spike threshold at 1 millisecond, and run a simulation. Okay, let's go back here. What did we say? It was 860 times 2, huh? Whoops. 860 times 2. Okay, so there we are. Let me do an init. Let me get rid of these traces. Erase. And let me get out of keep lines. I'm not in keep lines. Good. So how am I, how am I going to place my stimulus at a location that is going to stimulate at the other end? Well, first of all, I need a new stimulator, don't I? I've only got one. And if I click on show shape, you'll see that it's at the 0 end of the axon. It says that right up here. It says there's an eye clamp at the 0 end of the axon, which is the left side. If we want to make a new one, we do Tools, Point Processes, Managers, Point Manager, and release the mouse button. Okay, now let me see here. Okay, I'm going to have to drag this down so we can see this. And I want to change, this is our new point process manager. Right now it isn't managing any point processes. I'm going to select point process and scroll down to iClamp. And now you see it's created something located at axon point 5. We'll move it from there in a second. We want the delay to be 1 millisecond. We want the duration to be 0.1. Let me go back over here. Show parameters. Yeah. We want the duration to be 1. I want that to be 0.1. Okay. User interface has gotten a little sluggish here. I can mouse around, but I can't change these. Show shape. At least I can move it over to here. No, I can't. Let me stop share for a moment. Okay, it looks like I'm back in business here. So now I have a there we go. Now I've got an iClamp located at the one end of the axon, and it has exactly the 1720. There we go. It has exactly the same parameters as the other iClamp does. The other iClamp is located at the 0 end of the axon. So we're going to be stimulating both ends, triggering spikes at both ends. And the spikes are going to, in the one case, one spike is going to propagate from left to right. The other spike is going to be propagating from right to left. And what do you think is going to happen? Do you think they're going to propagate through each other when they get to the middle? Are they going to blow up with a gigantic spike amplitude 2 times as big as it normally is? Or what? What's going to happen? Well, let's do a simulation and find out. Whoa. That was too fast. Stop. Let me make that a little bit slower. And let me cut the duration of the simulation to 15 milliseconds. Let me do that again. Init and run. So they met in the middle and they didn't propagate past each other. Is this a surprise to anybody? Did anybody anticipate that? Yes, it did annihilate. They annihilated each other. And why did that happen? What's going on? Why can't the one spike coming from left to right continue past the midpoint? Why can't the one coming from right to left continue precisely? Inactivation of sodium channels. That's right. And persistent activation of potassium channels. Okay? So we can actually plot those if we like. Okay, so I'm going to bring up a graph with why don't I bring up a graph that shows the channel conductances. Okay, so actually I want a space plot. Oh dear, things are getting iffy again. Close. Graph. Shape plot. And if I want to plot, I'm going to try to plot a different variable. It'll be the sodium conductance. And of course now, except that's not working. Oh, it is working. Okay, so now I can try to do a space plot of sodium channel conductance. Okay, so this is sodium channel conductance plotted as a function of distance along the axon. Okay, and if I do this, let me do an init, and I'll continue for a couple of milliseconds here, and I will do view equals plot, and then I will do set view to go from 0 to 0.004. Let me see what happens here. Init, 1 millisecond, 2 milliseconds, already too big. 0.04. There we go. So let me do this again. Here we are. Init and run. And we watch. And indeed, the sodium conductance is collapsing. But why is that? Well, to find out why, we can plot, bring up another shape plot. But this time, I'm going to plot H. That's the inactivation gating variable, okay? And if I make a space plot of that, which I can't do now. All right, well, it's too bad. Well, you're absolutely right. It is the sodium channel inactivation that's killing us. As a spike passes our location, our sodium channels become inactivated. There isn't sufficient time for them to recover, and that is what's going on. Very, very annoying this is. Okay. So we could, as an exercise, do this. Let me see if I can do that one. I'll try this one more time. HH axon pi, tools, point process, managers, and automatically I'm already dead. Okay, quit. All right, it's got too many things happening here, and something's eating a lot of cycles, and I don't know what it is. I would say it's Slack. I'm killing Slack. Now what's happening? Well, I guess it's Zoom. Okay, well that's revolting. Can I even go further down in the slides? Okay, use Cell Builder to change nseg to 15 and run a simulation. Well, let me just do this again. change nseg to 15. Okay, that's under geometry. nseg is 43, 15. So now let's take a look at what we see when we do init and run and let it run slowly. Do a aha. That looks to me, let's do that again, only let's just run it for 10 milliseconds. And let's run it for a little slower. So where I'm sitting, it looks to me like these traces are made of a bunch of straight line links, and we're seeing them hinge. Are you all seeing that? Okay. And that's happening because I've reduced spatial resolution, and now I'm not quite capturing the curvature of the dependency of voltage in space. I can see it's there kind of, but I would be missing details. Okay. Okay, using the original value of nseg, determine conduction velocity over the middle half of the axon. Okay, so how would we determine the conduction velocity over the midpoint, over the middle half? Well, one way to do it, I missed how to put a point process manager on a selected spot on the axon. Where can I find that info? Well, practice, as they say. Practice is what does it. If you have a point process manager and it's behaving properly, you should be able to use, once you've chosen what kind of a point process it's supposed to be, you can go to show shape, and if you click on the shape wherever you want that point process to be located, it'll move it there. Okay, and that's how you do it with a graphical user interface. Okay, good. And we covered that last time, and that's why there's a video of that up for you to review. It won't stick in your head unless you practice it. Okay. So now, how are we going to measure conduction velocity over the middle of the axon? Why do I want to measure it over the middle of the axon? Why don't I just say from one end to the other? Well, we can look at these waveforms here and we see, as somebody's already pointed out, this one's a little peculiar looking. It doesn't look right. And even if I change the duration to 0.1 and the amplitude to 860 times 2, it still looks a little different than the others. Okay. The channels near the stimulus electrode are getting exposed to a different time course of membrane potential than the channels out here are. So the state of these channels in the first part of the axon will not be the same as the state of the channels further down the axon when the spike starts propagating. And that means that the amplitude of the spike will change a little, the shape of it will change a little, and its conduction velocity will change a little initially. Then in the middle of the axon, it'll sort of settle into a more or less constant waveform along a substantial part of the axon's length. Then as you get to the distal end, the charge that's leaking into the axon and the depolarizing charge, which is helping propagate the spike forward, is going to be piling up in the distal end of the axon. And that's why this spike is a little higher in amplitude than these two, okay? We have depolarizing charge spreading down the length of the axon ahead of our spike. And as it gets to the sealed end of the axon at 20 millimeters distance, 20,000 microns here, there's no place for it to go except through the cell membrane. That's why this is a little bigger. So these channels at the distal end get a little extra depolarization a little quicker than the channels did in the middle. So the spike propagation velocity will increase a little bit as you approach the sealed end. So if you want your conduction velocity measurements to be unaffected by these end effects, you want to be measuring conduction velocity along the middle part of the axon. So how could we do that? Well, if we could place recording electrodes at different locations along the axon, we could plot the time course of membrane potentials at those points, and then we could find where they cross some kind of a threshold level. Now, how can we do that? Well, we would like to have a voltage axis graph that does that. And here we've got one already, but it shows us 3 points, okay, but not the ones that we want. We want something that's in the first half of the length of the axon and something in the second half. And I could make a wild guess as to where I could place things, but no, it wouldn't tell me actually where it went. Why? Well, because I don't know where the centers of the different compartments are located. There's 43 of them. The axon is 20,000 microns long. Dividing 43 into 20,000 and then trying to figure out where the centers of compartments are is a little bit messy. I would rather let Neuron do this for me. So what I'm going to do is I'm going to bring up a shape plot, and I'm going to use this shape plot to create what we call a time axis graph or a time plot. So in this shape plot, I click on the menu square, scroll down to time plot. And you see this little V over here. Anytime I click on the axon, it'll add a new trace to this new graph. You know, I don't automatically get a plot of membrane potential at the midpoint of the axon, and now it's added a trace recorded somewhere over here to the left of the middle. And now I'll click over here, and now it's added a trace that's being recorded somewhere to the right of the middle. But where is that somewhere? Where is that located? Well, let me just do move text, and then I can grab these labels, V of 0.3 and V of 0.76. Ooh, look at that. That's interesting. So I know now, I have now the locations of 3 points, and if I run a simulation, I see the membrane's potential at those 3 points. They are far from the ends, so they're not corrupted by the sealed end effect, and they're not corrupted by the stimulus current injected at the zero end. Okay, so I can measure where these cross, say, the x-axis, the time axis. So let me just do crosshair, and now I can click on axon V.3 trace and find the closest point to the x-axis crossing. And I can do the same thing on this blue trace. Find the closest x-axis crossing right there. That's pretty good. Now let's look down here, and we see that the times at which these crossings are shown right here. So the time it took that spike to propagate from 0.3 to the 0.766, whatever it is, location is 5.25 minus 2.575, or 2.95 milliseconds. Now all we need, wait a second. That's wrong. I want it on the way up, not on the way down. So let me see, on the way up. There we go, that's better. It's 4.275 minus 2.575, and it's 1.7 milliseconds. Okay, now in order to know what the conduction velocity is, I need to know the distance. Okay, so what is the actual distance between those two? Okay, well, we know that the length of it is 20,000 microns, so 0.3 times 20,000, and 0.766 yada 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 times 20,000. So it's 20,000 microns times 0.766667 minus 0.3. So that's the number of microns. And if we do that, divide by 1.7, and we get that many microns per millisecond. 5,000 microns per millisecond. Okay. Or 5 millimeters per millisecond, or 5 meters per second. Okay. We could directly plot V of 0.3 and V of 0.7 on voltage traces and scale with regards to the length. Do we know that in fact we can record from 0.7? Do we know that? For seg in axon, print seg x. Whoa. For seg in h dot axon. That's what it's called, h dot axon. Print seg of x. Okay, h dot axon. Okay, h dot axon dot l. Seg equals h axon 0.5 seg x. That's vexing. Seg.x. There we go. That's better. Well, why is nseg only 15? It should have been 43. Okay, well that's because I changed it with the cell builder to be 15. I never went back to 43. Yes, the reason, you're absolutely right, Neil. We could directly plot V of 0.3 and V of 0.7 because this particular axon had discretization parameter of 15, and it would have centers at 0.1, 0.3, 0.57, and 9. I meant to restore nseg to 43. My mistake. In general, If you're using NSEGs that are scaled according to the length of your sections and the biophysical properties of their sections, they'll have odd values, but they won't be nice odd values. If it's an odd value that's a multiple of 5, it will definitely have segments centered at 0.1, 3, 5, 7, and 9. And that's really nice. But to get what would be adequate spatial discretization for this particular model cell, for this particular axon, I should really be using, instead of a NSEG of 15, I should be using 43. And if it was 43, I would not have known, there would not have been a nice number, the 0.3, 0.5, 0.7, to specify the position of a segment center. So that's why that would not work in general. Okay. Yes, this wouldn't be generic. 0.7 and 0.3 would not be generic. So what we're doing is we're discovering where the segment centers are by having clicked upon the shape plot, and it's creating automatically a new trace. Okay, when I do that, see, I just created a new one with this hideous green color, and it says it's going to be at 0.2 something. Okay, and if I move the text, I could see what it was, but I'm not moving the text. All right, so much for that. Okay. Now let me quit so that I can get control of the slides again. Okay. All right, so this is what I got earlier. And let's change iClamp duration to 10, adjust the clamp to, this is a good one. So let's do that with our squid axon. So I'm going to run Python 3 axon pi again, and I'm going to change, it is an iClamp already. I'm going to show the parameters. I'm going to make the amplitude, say, minus 10. Let's try it at minus 10 nanoamps and let the duration be 10 milliseconds. And let's see what happens if we run that simulation. Okay, I'm going to make t-stop be longer, be 50. So what happens here? I'm hyperpolarizing the cell a little bit, and I'm looking at something peculiar here. Let me do view equals plot, and you'll see where I'm injecting the hyperpolarizing current, the cell hyperpolarizes, and when I stop the hyperpolarizing current, it overshoots a little bit. Okay, it started out at minus 65, hyperpolarizes a little bit, and when the hyperpolarizing current is stopped, it overshoots. Okay, let's make that stimulus a little bigger. Knit and run. Do another view equals plot here. The overshoot is bigger, and it's a depolarizing overshoot. Okay, I've gone from minus 65 to minus 73. Let's try to get it to be minus 75. Or what does it say? Minus 80? It says minus 80. Okay, so let's try to make it be minus 80. Okay, view equals plot. Let me see here. Where did we get to? Crosshair gets down to about minus 75. So even without getting it down to minus 80, when I stop the hyperpolarizing current, the cell bounces up and a spike is triggered. Okay, So what's that called? Who knows what that is? Hello, hello? What is that? What is this phenomenon called? It is a rebound spike. Yes, it's called rebound excitation. And it is also called anode break. And anode break has a long and honored history. And in fact, it was known in the late 19th century. I can get you the citation, a citation of a paper that cites another paper that refers to the late 19th century. So let me go back here. And let's get you the whole thing. There's the whole citation from Journal of Physiology, 1956, volume 131, page 243. Okay. And in fact, it is cited here in this slide. And if you go to this DOI, you'll be able to get Journal of Physiology's paper. Okay, the actual paper, you get a PDF of it scanned. Okay, what's happening? Why is that occurring? Why does anode break excitation occur? Well, see if we can do this. See if this will work. Okay, so let me stop that and let's initialize and let's go back to 20 milliseconds and let's just do that again. I'll run it for 1 millisecond, that's things are just at a baseline state, and then I'll single step our way through the stimulus. We're hyperpolarizing the cell, and you'll notice here that as I hyperpolarize the cell, what's happening to these gating variables? Well, we notice that M is collapsing towards 0 at the 0 end. We'll notice also the potassium current's N gating variable is also reducing, and we'll notice that sodium channels H, or inactivating gate, is recovering from inactivation. Okay? So what is this doing? We're closing potassium channels, so we're eliminating one of the ways that holds the membrane potential at near EK, and we're removing inactivation from the sodium channels, so we'll have more channels, most sodium channels will be available to open, okay, when the cell finally is released from hyperpolarization. And we see how this happens not just where we're injecting, but it happens over a substantial length of the axon, okay? We're shutting down potassium channels over thousands of microns of the axon, and we're allowing sodium channels to recover over thousands of microns. Okay? As we go along here. And if we continue for another millisecond, you can see how much, when we started, 40% of the sodium channels were inactivated. And now, as we go along here, we have now removed inactivation from half of those. So we're up to almost 80% of the sodium channels are primed, they're ready to go. Meanwhile, you'll see that ionic currents themselves don't do very much. If we now continue, and we get up to 11 milliseconds, I'll continue for a millisecond at a time, the cell's membrane potential very quickly returns toward its resting level of minus 65. It just takes a millisecond to do that. Okay? But notice that none of these gating variables changes very quickly. Even though membrane potential has jumped a lot in 1 millisecond, none of these has changed very fast. That's because they have very long time constants compared to a millisecond when the cell is hyperpolarized. Continue for another millisecond, and you'll see that as membrane potential still hangs around in the vicinity of rest, we're seeing that some of the sodium channels are starting to activate. We're getting M is increasing. And at this point, the depolarization is happening so fast that sodium channels are opening quicker than the potassium channels are. We can see here that sodium current is growing much more rapidly than the potassium channels are. We can go back here and do this 1 millisecond at a time. There's that 1 millisecond during which the membrane potential returns to rest. Another millisecond, another millisecond, another millisecond. Now we see the sodium channels start to activate very quickly, and the sodium current grows very rapidly, outstripping the growth of potassium current. And that's what's causing this acceleration, this upward acceleration of membrane potential. And we continue for another millisecond, and boom, there's our spike. Okay? And that will continue to propagate along the axon. Okay? Now, why is this called anode break? Does anybody know why? Well, the original experiments that were done on axons, on all tissues, used extracellular stimulation. And nobody had glass microelectrodes that they could use. There were no patch electrodes. There was no ways to get fine electrodes into the inside of cells. And what they could do is they could attach metal plates or pledgets of gauze soaked in saline to electrodes and batteries, and they could apply these stimuli to the outside surface of things. And the positive side of the battery, of course, is the anode of the battery. And so the electrode that was attached to the anode of the battery would be the one that would go positive. And if you're making the extracellular fluid more positive compared to the intracellular fluid, you're hyperpolarizing the cell. You're not making the inside of the cell less negative, you're making the outside more positive. And that hyperpolarizes the membrane. That closes down channels. Then when you release that, when you break the connection of the anode to the battery, all of a sudden the extracellular potential drops back to 0, and the transmembrane potential is depolarized. And the cell can reach firing threshold. And there you have anode break. Okay, I think that takes care of all the questions that were asked. I'm sorry that the user interface at my end got so slow that I wasn't able to do these exercises as quickly as I would have liked. If you have other questions, please feel free to post them here in the Ask Tutors part of the of Slack. If there's other questions that haven't been addressed for you, let me know. Let me know by email, or better yet, by Slack. I think somebody asked, what about changing points plotted per millisecond instead of DT? You can change points plotted per millisecond instead of dt, but you have to make sure that the dt value that neuron chooses is going to be small enough to give you good temporal accuracy, and small enough typically means on the order of 20 to 25 microseconds. Sometimes for some very fast processes, you need to make it faster, like on the order of 10 microseconds or even 5 microseconds. But for the things that we've been doing and are going to be doing over the next couple of weeks, the next month actually or so, 25 microseconds is fast enough. Let's see, other questions? Again, this is all procedural knowledge that we're using to do this user interface construction and working with things. And this does take practice. You won't remember it unless you do it. The videos are available. The slides provide some help with that. If you want to be facile with the graphical user interface, you just need practice. Okay. Again, the point of having a graphical interface is that you can do quickly things that shed a lot of insight into what's going on. And I was able to create these graphs before the course started, before today's session started, very quickly, and use them to explore what was going on in accounting for anode break excitation. All right, we'll be sending out invitations to next week's, to Thursday's, day after tomorrow session, and there's no homework in the meantime. If you want to go back over the things that we did today and last Thursday, by all means do so. If you have questions, post them on Slack or email me, okay? And thank you very much, and I think that we will end the session here. All righty, bye-bye and stay well.